In this video, I'm going to discuss with you properties of the distribution of sample means. I'm going to speak with you about something called the central limit theorem and talk about some properties of the DSM, shape, mean, and variability. So we can identify proportions in the distribution of sample means because it assumes the shape of a normal distribution. And as you will recall from our unit normal table, we can talk about the proportion of scores, and in this case, the scores are means, at any particular point in the distribution because it is a normal distribution. The central limit theorem is a mathematical proposition. It is actually the cornerstone of inferential statistics. So what the central limit theorem does is it describes the distribution for any population, no matter the shape, mean, or standard deviation. So we have a population, and when we take all the possible sample means, the central limit theorem is what allows us to describe this normal distribution that results. And as the sample size approaches 30 of the samples that we're drawing from the population, a sample distribution approximates a normal distribution. So, according to the central limit theorem, the parameters of the distribution of sample means, the DSM, has three components: shape, central tendency, and in this case we're talking about the mean, and dispersion or variability, and in this case we're going to be talking about something called the standard error. Now this might all be sort of Greek to you at this point. Take good notes and stay with me. So I'm going to review some of our symbols that we've been using and introduce you to new symbols for the DSM. So when we have a population, we've been using the Greek letter mu to talk about the mean and the lowercase sigma to talk about the standard deviation. And populations can be normally distributed or they might be skewed. Sometimes we have distributions that are skewed. Remember, salary data, for example, can be a skewed population distribution. But when we're talking about a mean and a standard deviation using these symbols, we're talking about of individual scores, right? So then we also have samples, and we had some different ways of noting sample, mean, and standard deviation with the capital M and for the mean and S for the standard deviation of, of a sample. Now samples can also be normal or skewed. And again, when we're talking about the mean and standard deviation, we're talking about individual scores. Things start to change when we talk about the distribution of sample means. This is a different distribution altogether. And we use this symbol right here, which looks like the mu with an M below it. And we're going to call this the expected value of the mean. And underneath this, we have what looks like standard deviation, but we have an M next to it. And this is going to be our symbol for standard error. We call it standard error of the mean, but I'm just going to call it standard error. So that's going to be the shorthand for it. So we talked about populations and samples could be normal or skewed, but the DSM is normally distributed. It is a normal symmetrical distribution. We talked about populations and samples talking about individual scores, but the DSM talks about mean scores. So we're talking about sample means, not individual scores. Hopefully that helps a little bit. So the shape, the DSM will be normal. And this is what the central limit theorem tells us if either of the following two conditions are met. So if the population from which a sample is selected forms a normal distribution, then the DSM will be normal. Also, if the size of the sample is relatively large, the DSM will be normal. And we say relatively large, and I mentioned this before, 30 or greater. So if we're dealing with a sample in our study that has 30 or more individual participants in it, then we can assume that the distribution of sample means for our study is going to be normally distributed, and we can do all sorts of things with that. So that's why when we're doing research, we really do want to have greater samples. Now, if it only takes 30 for it to approximate a normal distribution, it only gets even closer to a normal distribution with the the higher number we have in our sample. Greater samples lead to a more normal distribution. So as our n gets larger, and I've already said this, the distribution becomes normal regardless of the original shape. So let's say I had a population that had a skewed distribution, and I drew a sample of over 30. Well, all the possible sample means from that population would be normally distributed. The shape, both conditions do not need to be satisfied. So only one condition needs to be satisfied. So when we're doing our learning checks, read the scenarios carefully. The sample either has to come from a normal population, it has to be normally distributed, or the sample has to have at least 30 individuals. Now, very often we don't even really know if it's a normally distributed population. So for us as researchers, being able to have at least 30 people in our studies, or 30 samples, or 30 individuals, not 30 samples, 30 individuals in our study, helps us to ensure that the distribution of sample means that we're going to be positing will be normally distributed. So the measure of central tendency that we're using is the mean. And the mean of the distribution of sample means is identical to the mean of the population. So the mean of the distribution of sample means is called the expected value of m. And the sample mean that we draw is expected to be near the population mean, so a new mean is not required. So when we take all of those random samples from a population and theoretically plot them out mathematically, the mean will be equal to the mean of the population. So if you don't understand this yet, hang in there. Write this down. The mean of the distribution of sample means is identical to the mean of the population. So I'm coming back to this symbol for standard error. This is the measure of dispersion that we're going to use, and it's a standard deviation of the distribution of sample means. So when we talk about all of these possible sample means that we can theoretically plot out, the means will vary from the population mean on average by the standard error of the mean. So it's the standard deviation of the DSM, and it's called the standard error of the mean. All right, let's take a look at the next video. We're going to talk about standard error in greater detail.